Hi, everyone. We're here to talk about vector fields and line integrals. First thing on the docket, though, vector fields. Um, yeah, a vector field is going to be a kind of function here. Let me get my mouse. Hopefully you can see this. Yeah, it's going to be a function. It's a multivariable function that has two inputs, and it's going to output a 2D vector. At least, this vector field is 2D to 2D. We're going to look at some vector fields that are 3D to 3D. But what it boils down to is that imagine that at every point in the plane, so every point in the XY plane, you draw this two-dimensional vector. And so, when evaluated at a point, this will just be two numbers inside of a vector. Let's go ahead and look up at figure 1 and figure 2 here. These are some examples of, it's some examples of the same vector field. One is scaled and the other one's not. So figure 1 might be how you would initially start graphing a vector field if you'd never done it before. And I don't know, maybe we look over at this point. Yeah, this blue one. I'll make it a little bit bigger. Shoot, that point looks to be at around 2/3 in the X direction and maybe negative 1/3 in the Y direction. And what we're doing at every point in the plane, we are plugging this X value and Y value into the vector field so that when we create our vector, we would be, if for this particular vector field, we're going to put the opposite of the Y value in for the X value of the vector, and the X value comes second. All right. So that when we draw the vector up here, we are going 1/3 in the X direction and 2/3 in the Y direction. And so that's what's going on all over the plane in terms of figuring out how to draw these vector fields. But figure 1, it is cluttered. The vectors get very long and they start overlapping each other. It looks gross. So very often we end up looking at scaled versions of vector fields so that the vectors don't overlap and they have a nice, pleasing aesthetic quality. So figure 1 and figure 2 are really the same vector fields. This one's just been scaled down so that the vectors look more friendly. So yeah, in this particular vector field, it looks like we're getting some kind of counterclockwise rotational kind of motion here. And that actually makes some sense. Yeah. This is kind of like XY, but rotated to the left 90 degrees. Cool. So introduction to, okay, vector fields exist. Let's take a look at some examples. Really, we're looking at vector fields here. Well, I mean, because vector fields show up in a lot of different places, we're going to look at some examples soon. Okay, example number 1. Describe this vector field and sketch F, the force field, with representative vectors. Okay. So the numerator of this fraction is a vector. This vector xy, we could think about, if it's plotted at a point xy, maybe I should just start the sketch right now. Oh, and I put these grid lines on the background, so hopefully I could make straight lines as I sketch things. We'll see if that works. Oof. All right. Um, cool. So if we're at a point xy, let's pick, I don't know, 2, 1. Let's say we're at the point 2, 1, and we want to draw a vector. Well, this one's actually pretty easy because put our x value in for the x value of the vector and our y value in for the y value of the vector. So the vector just becomes 2, 1 as well. And you can, try this yourself, but hopefully after plotting a few of these, you would kind of see that these vectors tend to point directly away from the origin. Let's point one down here. And their length is actually the same length as the distance away from the origin where the point is. So yeah, if we were just drawing x, y, we would have a bunch of vectors pointed away from the origin. So I'll go ahead and write, vectors pointed away from origin. And then we've got to think about the other part. The denominator says that we're dividing by 2 times the magnitude of the vector. So dividing by 2 times the magnitude of xy, which we know to be 2 times the square root of x squared plus y squared. What does that mean? So at every spot, the length of each of these vectors is going to be scaled. If it was just scaled by the magnitude, then they'd all be unit vectors. But since it's scaled by 2 times the magnitude, they're all going to be half unit vectors. So what this is going to say is all the vectors have length 1/2. And so I would update my previous drawing, or my previous drawing where we were just plotting x, y, and now we would say that at every point, no matter where they are, all the vectors are being scaled to be of length 1/2 instead of, whatever length they used to be. So yeah, that's that. And I think I have this on GeoGebra. I might have to get out of this. Okay. GeoGebra's been a little not cooperative this morning. Okay. Oh, see, look at, I shouldn't have said anything. Come on, GeoGebra. Anyways, on a good day, hey, all right, fine. Whew, this would work. I've got a representative vector here. This is what the vector field could look like. And notice, like, we can't possibly fill every single point in space with a vector because then it would just look like a big old mass of, well, pink in this case. But normally we graph these vector fields on a, grid squares on a lattice. Okay, so that's that first example. Let's open this back up again and move on to example 2. Describe the vector field that looks like this and sketch F with representative vectors. I don't know, this one's pretty boring. I mean, it's our first 3-dimensional vector field, but what we would be imagining is that at every point in 3D space, we would have vectors that are pointing straight up. 0, 0, 1 means we're going in the positive z direction. Let's see. GeoGebra, I believe in you. Opening file failed. All right, so I left some of these open so that, no, that's the next one. I left some of them open so that hopefully they would just stay open and work. All of the vectors are just pointed up, and there's a whole field of vectors. We're going to look at more complicated ones. Yeah, I'm not going to get too flustered about example 2 not working. All right, next one. Here are just some examples of real life vector fields, wind patterns, over regions of land could be examples of vector fields. Wind around an airfoil could be another example of vector fields. Some more real life examples of vector fields. Here we've got Newton's law of universal gravitation and describing gravity using gravitational field. Yeah, we're looking at the force of attraction between an object of relatively small mass m and relatively large mass capital M. G is gravitational constant, and little r is the distance between two objects. One thing I want to highlight here is that they've introduced the notation of letting a bold r be the vector xyz. That's not something that I'm going to do too frequently because honestly, we use r for just a ton of things in this class. And I don't want to introduce another one, but this is just shorthand for the vector xyz. So yeah, I mean, this is the force field. Here's the magnitude of that force field. This is what it looks like. I'm not going to ask you guys to work with gravitational fields too much, but it does make for a cool picture. I think this is one that I had saved up in my other tab. No, that's the gradient field, gravitation. And look, come on, GeoGebra. Are you real? Okay, good. Gravitational field. You can see something wonky happening in the middle, but yeah, this is one of those inverse square laws where the force that you would be experiencing varies inversely with the square of the distance away from the object that you are. So all these vectors away from the center are smaller than the vectors that get closer to the center. Cool. Gravity. And very similar to that for all you electrical engineers. Yeah, like there are electromagnetic fields as well. So we've got electric fields, Coulomb's law. Oh yeah, right up your alley. And so, yeah, this is what a repulsive force field might look like. This is what an attractive force field might look like. Well, gravity was obviously attractive. But yeah, Coulomb's law could be repulsive. Cool. Another example of vector field. Mathematically speaking, here we get to the interesting stuff. Remember that we worked with gradients in this class, and a gradient is a function that can create a vector field because what a gradient does is it takes in two variables and a function f and spits out a partial derivative with respect to x and a partial derivative with respect to y that are components in a 2D vector. So gradients can be used to create vector fields, and we call them gradient vector fields. One thing that's important to remind ourselves, or new vocabulary at this point would be that the function f in this case would be called a potential function. Cool. And we'll be looking for potential functions as we move through this. Okay, so determine the gradient vector field of the scalar field, blah. So yeah, they're calling this a scalar field because we've got two inputs and one output. So the output is a scalar. But yeah, if we wanted to look at the gradient vector field, all we need to do is take the gradient of xy. Partial derivative with respect to x would be y squared minus 2x. And partial derivative with respect to y would be 2xy. And that's it, because the other part just goes away. Yeah, okay. That's pretty boring. I mean, that is the gradient vector field. Oh, the picture is actually not boring though. Let's see if this works, because we'll be able to look at the potential function and the vector field at the same time. If this opens correctly, we're waiting. Good job, GeoGebra. Okay, I mean, to be fair, I am asking GeoGebra to do a lot today. Okay, in the teal, we have our potential function x y squared minus x squared. And it gives us, this whole thing with a saddle point in the middle. That's pretty cool. I've created these horizontal level curves in order to, be able to look at level curves when we look down on it from above. And I've plotted the gradient field here in the XY plane, because again, the gradient's going to be two-dimensional in this case, because we're working with a function that takes as inputs two variables. But yeah, this is a gradient field, and gradient fields have some cool properties. Yeah, one is that all of these gradient vectors, like we expect, are perpendicular to the level curves. Another one that we're going to learn soon is that these gradient vector fields are called conservative, and the fundamental theorem of line integrals is going to apply to them when we get to section 15.3. So yeah, gradient vector field. And in the teal is the potential function that created that vector field. Cool. All right, we back. Example 6, we're making time. I wrote f as a potential function just to remind myself, if I hadn't said it already, to say it. We're looking at the gravitational field. What we're trying to do in example 6 is show that the gravitational field is conservative. A conservative vector field can be written as a gradient field, and therefore would have a potential function that could generate it. Yeah, one of the things maybe that I didn't mention is that these conservative vector fields have a special meanings in like physics, meaning that like these vector fields represent things that like obey physical laws, like conservation of mass and energy type of stuff, where the vector field might show potential trajectories for an object, but it's not necessarily a field that's adding new energy to the system, if that makes sense. So like gravity is an example of a vector field that's conservative. And yeah, what we'd be looking for is a potential function f that would have as a partial derivative with respect to x this partial derivative with respect to y, this, partial derivative with respect to z, this. And so, yeah, what this would look like is taking antiderivatives. And yeah, if you think about taking antiderivative where yeah, this is, I mean, with respect to x, there might be, kind of a chain rule kind of thing going on here, but power rule means you're adding one to the denominator's exponent, and yeah, this is the kind of function that would give you this when taking the derivative with respect to this. So, yeah, a potential function does exist, and if you take partial derivatives of this with respect to x and y and z, you would get these components of the gravitational field. So there's a potential function that could be used to make the gravitational field. Cool. But yeah, we're going to focus on practically some simpler examples than that. What time are we looking at? I don't think that we're going to end up doing this homework for realsies. I might give you the opportunity to do the activity as like extra credit. Anyways, it would be a good opportunity. This is the kind of thing that I could, potentially put on a final exam. So it would be good for you to kind of maybe pause the video, check your understanding, and think about if you could start to match the vector fields that are given here to pictures that are below. Yeah, this is a kind of problem that could show up. Cool, go ahead and do that. And now I'm going to assume that you've done that. And yeah, I'll try to go through these somewhat quickly because really we want to get to the line integral soon. Cool. So, which one do we want to look at? All right, let's look at 11. 11. We see y in the x component and negative x in the y component. One thing that you might notice about this vector is that if you took its dot product with xy, you would get xy minus xy, which is equal to 0. So what does this mean? It means that the direction of the vector is perpendicular to the vector that would get you to the point where you're at. And so this one represents a vector field that has some rotation. I mean, if you really wanted to just look at these all, you could just plug in x and y values and start to make matches based on the vectors that look like they match what you have. You could just go point by point and figure this out. But yeah, looking at the dot product here kind of gives us a sense that all of the vectors are kind of perpendicular to how you would get to the points from the origin. And yeah, so this one's B. It's the one that rotates. Let's go with, let's go to number 12. X and minus y. So we're going to be going in the same direction as whatever x value we're at, and we're going to go in the opposite direction of whatever y value we're at. And so this one ends up being D. Notice that as you go farther out, the x values get more pronounced in all of those vectors. And the higher up that you go, the more down that the vectors go, the lower that you go, the higher that the longer vectors that are pointing up. And so that matches D. 13, we've got X and E to the Y. So X means that the vectors are going to be pointed in the same direction as kind of the point that they start at. So they're going to be pointed away from the origin in the X direction. And in the Y direction, we've got E to the Y, which will approach 0 as Y approaches negative infinity, and will get very, very big as Y approaches large numbers. So A fits that description. It's got the X values going in the same direction as X values, and it's got Y values getting very big up here, almost 0 down here for the Y values. So boom. And then, yes, by process of elimination, no, we've got this one for C. Some notable things here, since we've got almost the vector xy on top, it's only different from xy by saying x minus 1. What that effectively does is it makes x equal to 1 kind of behave like the new origin. So on this one, x equals 1 is behaving like a new origin, and what we're doing is dividing by the magnitude on the bottom. So all of these vectors are unit vectors. So cool. All right. Next part of what would be on the homework are these two problems. We're going to try to decide whether these vector fields are conservative. So if these vector fields were conservative, we would have a vector where we've got the partial derivative with respect to x and a partial derivative with respect to y. And it's been a while since we've invoked Clause's theorem, but if our potential function is well behaved, the mixed partial derivatives should match. And in this case, if we looked at our partial derivative with respect to x and then take the partial derivative with respect to y, we would get 1 for this one, because the partial derivative of y with respect to y is 1. And if we went over to f of y and then took the partial derivative with respect to x, this one would be y. And so these mixed partial derivatives don't match, and we have no hope of a potential function. For the second one, to make things interesting, we are going to have a potential function. So if we took both the partial derivatives, so if we were treating this one like, well, we can do the same color. Yeah, sure, we'll do it. If we took the partial derivative with respect to y here, good grief, it's a product rule. Oh, it's going to be product. Well, actually, wait, no. It's not a product rule. Yes, it is. Yes, it is, because we're taking partial derivative with respect to y. Blah. You know what? This is an exercise for you. You could take those partial derivatives and show that they're equal. I don't want to do that. One thing that might be slightly more interesting, though, is actually, so once you found that they're equal, that tells you, oh, hey, let's find a potential function. So if we have the partial derivative with respect to x and the partial derivative with respect to y, we've done this before what we can do is take the antiderivative of the partial derivative with respect to x, and we're going to want the antiderivative over here to match the antiderivative of the partial derivative with respect to y. Good grief, 2xy cosine xy squared dy. So we can take both of these indefinite integrals separately. Goodness. On each of these, it looks like a u substitution is in order. If we make u equal to xy squared, then du, when we're going with respect to x, would be y squared dx. And so, this y squared dx will get canceled when we go integral of cosine of u du. Cool. For this one, again, I think the same u is in order. Du would be, we're taking derivative with respect to y, so 2xy dy. That matches up with what's left over here. All of that is a good sign. So that on the right-hand side, we're going to have cosine of u du. Cool. And I mean, on both of those sides, when you take the antiderivative, you get sine. We'll get sine u plus c. Now, in this case, it's possible to have a whole function that would be in terms of x here, or sorry, in terms of y, that would have just been erased when you took the derivative with respect to x. So like there could be some g of y as our plus c over here. Good grief. There could be some h of x as plus c, but what this ends up happening, I mean, since these two things are equal to each other, that function of y or that function of x is totally equal to 0 because those things need to be equal. And so sine of u becomes sine of, xy squared is what we should write. And that's what our function is. So our potential function should be, just kidding, sine of xy squared. Cool. And then if you took partial derivatives of that function, it should give you what was there before. All right. We've got to move. We're getting to, section 15.2 on line integrals. All right. Take a break. Pause it if you need to, but we're going right in. Line integrals. These are going to be a lot like the arc length integrals that we did back in chapter 12. And I remember that you guys really liked the arc length integrals, so this, I'm sure, is going to be popular. Arc length, back all the way at the beginning of the semester, we were working with our arc length differential ds. That's coming back. Remember, though, that our arc length differential is really the magnitude of the tangent vector times the change in t. So with these line integrals, a constant theme is going to be taking the information that's given to us and trying to express everything in terms of parameter, and that'll almost always be t. So we're going to try to give everything in terms of t as we do these line integrals. But yeah, instead of just adding up basically a bunch of magnitudes of tangent vectors, like we were doing in arc length, so adding up a bunch of tangent vectors to get the length of some kind of arc. In a line integral, what we're doing is adding up a bunch of weighted points along a curve. So yeah, just like when we were doing double integrals, triple integrals, and I don't know, if we were going to try to find the center of mass of objects that were 2D or 3D, double and triple integrals allowed us to put functions that would represent objects of changing density throughout whatever shape we were integrating over. And that's the same kind of thing that's happening here. Instead of just having an arc that has a somewhat boring length, what we can do now is have a curve that has differing densities all along the curve, and those differing densities are given to us by the height of some function f. So what you would imagine happening is that we're integrating along a curve. In this case, the curve's in the xy plane, and the height of our function f of xy is giving us the weight of the point at each point on the curve. So here, when we're starting off and the function is kind of relatively high above the curve, we're getting a positive weight. That weight, gets smaller and smaller and smaller. It actually looks like around this point. Sorry, let me take a drink. Oh, all right, Rona. Yeah, around this point, it looks like that function that's giving us our height actually goes below the xy plane, and it starts sweeping out negative area underneath the curve that we're integrating along. So yeah, a line integral is a generalization of an arc length integral. And it allows us to weight different points on the curve differently. So yeah, it's going to be super fun. To look back at the notation, a line integral might be given to us by integral with a c at the bottom. That just means curve. F is the function that's giving us our height, and ds is the arc length differential that would travel along the curve. In practical terms, we are going to parameterize everything in terms of t, so that ds becomes the magnitude of r prime of t dt. So we're going to be calculating that to figure out the speed at which we're traveling along the curve. F of r of t gives us the height at each point along the curve. And A and B are the starting point and the ending point along the curve in terms of t. Cool. And hopefully this will make more sense as we get into it. We'll zoom in a little bit, I think. Okay, we're going to take an arc length integral. where our boundary function, our top height function, is given to us by y minus xy squared, and c is defined as the upper half of the circle, the unit circle, traverse counterclockwise. Cool. So I'm going to go ahead and I'll just copy down integral c. We've got f ds. But all throughout this, we're going to try to parameterize this in terms of t. So we'll have a starting boundary on t and an ending boundary on t. We're going to have, and that's primarily going to be given to us by the curve that we're trying to parameterize. So we're trying to go over the upper half of the unit circle. That's what we're going to be looking at for the bounds. F is our function. Our function is, well, right now it's y minus xy squared. But we're going to be looking to put that in terms of t as well, because we're going to want everything in terms of t before we integrate. And so, yeah, maybe this is, right now, I would call this is f of xy, but we're going to want to write f of r of t in the next step. And then this next part, we're going to look at r prime of t dt. I don't know, right now, we'll just leave that like that, and we're going to fill it in the next part. So we want to change all of this in terms of t, and in order to do that, we're going to need to parameterize our curve. So, yeah, to parameterize our curve, we've got the upper portion of the unit circle, and we're traversing it in a counterclockwise orientation. And so I think the parameterization, from polar coordinates, x equals cosine t and y equals sine t. Notice that since the radius is just 1, I'm not even writing that down. But yeah, that's a good way to write our curve. So if I wanted to write r of t, I would go cosine t sine t. Believe it or not, we've done this before. And yeah, if we wanted to get to be able to do the second part, we could take the derivative of this. The derivative of cosine of t will be negative sine t. The derivative of sine t will be cosine t. Yeah, and eventually we're going to need to take the absolute value. Why don't we go ahead and do that? The absolute value of, or the magnitude of this vector is the square root of negative sine squared plus cosine t squared. That becomes, well, sine squared plus cosine squared. And we remember our Pythagorean identities. And so this is the square root of 1, or just 1. So nicely, when we go to do this in the next step, r prime of t just becomes 1, and we'll have a dt there. Cool. As far as parameterizing goes, let's think about what our starting value would be and what our ending value would be. We are going counterclockwise, yeah? Okay, cool. So going counterclockwise, we would start off at t equals 0 and end at t equals pi. So when we go over here, we would go from 0 to pi on our integral. bounds. And then in the middle part, we actually want this to look like f of r of t. And so basically that means we look over at our vector r of t and plug these in for x and y instead, so that when we see y over here, instead of y, we're going to write sine t. I don't know if there's a great color for this. Purple. So we're going to go sine t and then minus cosine t times sine t squared. And so we have effectively changed this integral that had, no t's in it at all, into a bunch of things that have t's. And then, yeah, we'd be able to solve this integral. Uh, hmm, hmm. Probably the way to go on evaluating this. Let's go ahead and do this. We need to do it once. At this point, maybe this isn't super new material, but I would change it into two integrals so that we're just splitting it up over the minus sign. So we're looking at sine t dt minus cosine t sine squared t dt. This first one, no big deal. Integral becomes negative cosine t 0 and pi, and then I'm going to go ahead and throw that in. So negative cosine of pi would be 1, and then minus negative cosine of 0 would be minus negative 1, so that would be plus 1. I believe that this becomes 1 plus 1 for this part. But we never did this part. On this one, I think we can use a u substitution. U equals, let's go sine t, du equals cosine t dt. And then, yeah, we can throw that back in. We've got integral u squared du. And if we want to go back and make our bounds correct, we would plug in 0 in for t. Sine of 0 is equal to 0, so this bottom bound stays 0. And then we'd plug in pi. Sine of pi is equal to 0, so the top bound becomes 0. And the integral from 0 to 0 of whatever is going to end up being 0. And so in the end, I think this integral is just going to work out to be 2. So that will be, yeah, the value of this line integral. Let's go ahead and take a look at GeoGebra and hopefully gain some insight into what we just did. Come on. All right, we're going back here. GeoGebra. Oh, this one's so good, you guys. I don't want GeoGebra to fail on this one. You can do it. I believe in you. Okay, sometimes this has worked. If I copy this and I say, hey, I want to open this up. I go and I search in GeoGebra resources and it says, oh, hey, here's the one that you were trying to do, and then it fails again. You're killing me, GeoGebra. I swear these work. And I even do a cool thing where you can see the. All right. If these things aren't generating, I'm just going to close them so that we have less. That's the next problem. And it looks like that one loaded. So great. Let's close these. We're going to close all my tabs. Feel free to fast forward. I'm going to get this thing working. That one was an old one. Stop it. This one's an old one. No. Oh, wait. Not working. Come on. I knew that they weren't working, so I tried to pull them up. Rip. Just all of these. Sorry. Sorry. I tried to leave them up, but okay. That one's working, right? Ooh, this one's later. Come on. All right, so that one's not doing anything. Okay, we're going back to this, and we're going to click the link, and we're going to be so patient. Yeah. Hey, I've signed in like 10 times today. This is my thing. Let me see it. Open my thing. Opening file failed. Open. That's worked before. Let's see view. View? Oh. You know what? If this works, I'm going to take it. Please. I don't know why. All right. We've hacked the system. I think this is going to work. Please, can I move this? Oh, all right. Anyways, we have our upper half of the unit circle. And yikes, my computer is struggling. Right now, what it's trying to do is color this unit circle, because one way we can think of what we're doing with a line integral is computing a weighted arc length around this curve, where the weights at each point are given to us by the height of the function that we're referencing. So, all right, that's some good colors. I'm going to stop that. Let's look at the function that we're referencing. Okay, the function that we're referencing is this curvy thing. And to make it easier to look at, I made, boom, this surface that shows you, how high relatively we are above this. So you can see that the red portions on this curve are corresponding to low points, and the purple portion is corresponding to where the function is high above the curve. But yeah, you could visualize this with color. You could visualize this with height. Because, yeah, we're working with a 2D kind of domain here. When we move up into a 3D domain, we're not going to be able to visualize it as awesome as this. But yeah, this is what we're doing as we do a line integral. You're really finding the area of this purple region. But yeah, we're adding up a bunch of weighted points along a curve. Line integrals. All right, we got that one done. Let's go back out and get out of here. Cool. All right, that's our first example of a line integral. Second, here we've got one where we've got a three-dimensional domain. So remember, when we're working with functions that have a three-dimensional domain, it's not something that we're going to be able to visualize in 3D space. We would need 4 dimensions of space to be able to visualize it because we've got a three-dimensional input and a one-dimensional output. And so this one, we're going to really have to rely on the coloring. We're not going to be able to show the height as easy. This one, all right, we can do it. Not so bad. All right, again, we're starting off with, we're integrating around a curve. Our f is giving us a height, and ds is our arc length differential. But we're going to change all of the stuff into t's. Yeah, our curve is a line starting at -1, 2, 5 and ending at 2, 0, 1. Okay, so we've got a line. That means, well, all right, we're going to go r of t will be, and let's go ahead and move this down a little bit. R of t is going to be something that has a direction vector and a starting point. A starting point could be either of those points. Actually, you know, since they call this one the starting point, why don't we go with -1, 2, and 5 for our starting point. And the direction vector is going to be the vector that goes from -2, 1, 5 to 2, 0, 1. And so we need to do a quick calculation of endpoint, yikes, minus start point. Which would give us the vector 3. 0 minus 2 is -2, and 1 minus 5 is -4. So we've got 3, -2, 4 for our direction vector. And if we wanted to write this in a more component format, this would be 3t minus 1, -2t plus 2, and 4t plus 5. So both of those are the same thing. Cool. So we have our parameterized path. Yeah. So I don't know. Right now I'm just going to write what's generally going to go here, and then we'll fill these in. Okay, so already I think we could talk about the start point and end point of this. If we're making a line segment, starting there and ending there, when we plug in t equals 0, we'll get the start point. So start point being 0, good. And then when we add this vector to this vector, we should get the ending vector. So our t value there would be 1. So we should be integrating from 0 to 1 in terms of our t values. F of r of t, we could do that at this point. we're going to be throwing in 3t minus 1 when we see x. 3t minus 1. We're going to throw in negative 2t plus 2 when we see y. And we're going to throw in 4t plus 5 when we see z. Okay, so that's our f of r of t here. And then, yeah, we haven't figured out the derivative yet, but we can do that. Well, actually, the derivative here is going to be a nice bunch of constants. Let's go with blue. Our prime of t, it's going to be 3, negative 2, and 4. It's just our direction vector. The magnitude of this direction vector will be the square root of 3 squared plus 2 squared plus 4 squared. 9 plus 4 plus 16, 29? Square root of 29? I think so. Cool. And so we'll have all of this times the square root of 29 dt. Yeah, so we've got everything in terms of t now, and we would be able to solve this integral. Honestly, I'm going to do it. Feel free to fast forward if this part's boring. I think I want to collect terms. I want to throw the square root of 29 out in front. We're going to have negative 6t squared plus 6t plus 2t minus 2 plus 4t plus 5 dt square root of 29. We're going to clean this up. Negative 6t squared. We've got 6t, 2t, and 4t, all of them being positive. Okay. So that's 12t. And negative 2 plus 5 is plus 3. You know what? I don't want, if I ain't making errors, I don't want them to propagate. I'm going to look at what I prepared real quick, just to make sure. Negative 6, oh, no. There's a 4t on what I did before. That is a minus 4t. Good grief. All right, I missed the negative sign. So back up there on my direction vector, I wrote the negative sign on the 4 when I calculated what the direction vector was. I did not copy it over. So there are negative signs that I missed. Sorry. Negative 4t, and this part's going to be 8. No, it's going to be 4 because this is 8 minus 4. So plus 4t. All right, now we're square with what I did before. So yeah, square root 29. Yeah, we can go ahead and take antiderivative now. This would be minus 2t cubed plus 2t squared plus 3t, and we're going to evaluate it at 1 and 0. So yeah, when we plug in 0, everything's just going to go away. We're going to have the square root of 29 times negative 2 plus 2 plus 3. So 3 times 3. So 3 times the square root of 29 as our answer. Cool. All right, so this one's a little bit different to visualize because we're starting with a 3D input. Can't be visualized. That function can't fully be visualized in 3D space. So we're going to rely on color here. Yeah. Come on. What worked last time? Oh, I remember what worked. If this refresh doesn't work, we'll get there. Come on. It should. All of this should be fine. You know, line integrals aren't hard enough themselves. We need to add new complexity. Dude, this one's not even coming up with the options below it. There it is. View. What is... Yes. All right. I'm going to allow this to change. This is going to give us colors along our straight line. So what we're doing when we do this line integral, we are, summing up a bunch of weighted points along this curve. Some of them weighted heavier than others. This coloring is happening based on functions that look like this. They're very saddly because we've got x times y plus z. Right now, this is a level curve of the function in question. And at different heights, or like different level curves, I've got these to change with the colors so that they match with the color that I made it on the line. For instance, if we stop at purple, you would imagine that this function is kind of coloring all of 3D space, and the colors are happening in a layered fashion along these surfaces. So I don't know. Imagine that you've got a Pringles can and the Pringles have different colored chips. That's what's going on in terms of you would color the entire stack with different colors. Anyways, this one's purplish, so it should be intersecting this curve at a purple point and a purple point up here. Anyways, this is what's going on behind the scenes. But again, we're taking a sum, we're integrating a weighted line segment, or a weighted curve is what a line integral gives us. We're summing up values along a weighted curve. Yeah, that's good. All right, that's example number 2. Moving on. Yeah, this gives us a new power to find mass, first, second moment, centers of mass, radii of gyration, according to all these integrals, of things that look like space curves. So, I don't know, if you wanted to integrate over a wire coat hanger, we could do that now, and we could find the center of mass of a wire coat hanger. In this case, we've got this V-shaped object. It's kind of like an absolute value function. And yeah, in example 3, they work on finding the mass and centers of mass of this wire-shaped object of possibly variable density. In this one, it is pretty boring because they've just said that the constant density will just be 1. So there's not really much to do. I mean, when you find the mass integral, you've actually, yeah, it's pretty boring. The density, you're just, yeah. Cool. So you can find the center of mass of this thing now. Am I going to do that? No. We've got enough on our plate right now, just learning what line integrals are. But we could do this now. Okay. This is the last major section, and good grief, we are a little bit over an hour into this, I think. So I want to wrap it up so that I'm not taking up too much of your Thursday. The last major thing is a line integral over a vector field. And so this is still going to be a line integral. It's still going to be a weighted sum along a curve. But now, in order to determine those weights, instead of looking at a function to determine like the weight at each point or the height, we're going to look at the dot product of two vectors to determine the weight at each point. And so we've got our friend, the unit tangent vector coming back. This is our force field vector. And when we break things down into t's, this should look somewhat familiar, but what's new is that we have a dot product. And what this is saying is that at every point along this curve, what we're going to do is take a vector in the force field and take its dot product with the displacement vector, the tangent vector. And when we take that dot product, it's going to give us a value, which basically tells us at this point how well are the force field vector and the tangent vector cooperating. Because remember the properties of a dot product, if the two vectors will be pointed in exactly the same direction, then the value of our dot product is maximized because the cosine of 0 is 1. If they were perpendicular to each other, then the value at that point would be 0 because when two vectors are perpendicular to each other, their dot product is 0. If the vector from the force field and the displacement vector were pointed in opposite directions, then you would get negative values for their dot product. So yeah, the picture is going along a curve, and at each point on the curve, we're taking the dot product of the force field with the vector that's the tangent vector along the curve and seeing how well they cooperate. And that gives us the value at each point along the curve. All of this notation down here, it would become more relevant when we start to do like Green's theorem and stuff, but I don't even think we're going to get there. Really what we're going to be aiming for is changing things into terms of t. This, don't worry about it for right now. 2 examples, and I'm done. Example number 4 here. Determine the work done by this force field moving a particle clockwise along this quarter circle. So dot products are really good for computing work. And so we're going to see what this force field does in terms of helping to propel this particle along this trajectory. Okay, so for these line integrals over vector fields, a lot of times what you'll see is f dot d as kind of the shorthand. Here we go, f dot dr. But like we said before, we're going to break this out in terms of some parameterized curve r of t, and we're going to look at the force field evaluated along the space curve, and we're going to take the dot product of that with the tangent vector. Yeah, this part doesn't look good. I'm going to rewrite it. That's R of t. There we go. And so, yeah, we're taking a dot product between those two things. Okay, so in order to get there, we've got F, our force field. But what we don't have is a parameterized path, R of t. So let's go ahead. I'll use blue to match with what we've got going on here. Come on. R of t, since again we're on a unit circle, I'm going to use cosine t and sine t for our x and y values. But what's weird here, since we're going clockwise, we're going to be going t goes from pi halves to 0, which, you know, is not the way that we're used to seeing bounds. That's opposite of what we would normally like to see. If it bothers us too much to write it like this, pi halves to 0, we could reverse the bounds and put a negative sign out in front, and it would be the same thing. Okay, so we've got that part. We've got R of t, so we'll be able to do f of R of t. Let's go ahead and do that now. I'm going to do this in red because f of R of t is the red vector field that's going on behind things. Good grief. So we've got 5 times cosine t sine t and negative sine squared t. That is the force field vector. And we'll go with blue here. Again, this time we'll go light blue, but r prime of t is negative sine t cosine t. And we'll just throw dt there on the end. Yeah, but in order to get the integrand, we're actually going to take a dot product. Boom, boom, pi halves, 0. Okay, so we've got negative 5 cosine t sine squared t when we multiply, well, yeah, when we multiply the x components, and then we're adding that to I guess the product of the y components, but yeah, this will be cosine t sine squared t, because yeah, we got that minus sign out in front of the sine squared. And yeah, this actually simplifies to be not so bad. Oh gosh. I don't want to do too many crazy things at once, but I'm tempted. This is just going to become 6. So I'm actually going to pull out a negative 6 out in front, and we're just going to have cosine t sine squared t dt. And if I wanted to get really fancy now, we could do a pi halves on top and a 0 on bottom and have a 6 out front. so that we've got, yeah, cosine t sine squared t. And then I've got to do a few more steps to finish this one out. Okay, let's not make the arrow that big. There's going to be a u sub. Goodness. All right, I'll write the u sub down here. U equals sine t, du equals cosine t, dt. So that turns this integral into 6 times u squared du. And if we plug in the boundaries in for sine 0 becomes sine of 0, which is 0. And pi halves becomes sine of pi halves, which is 1. And so then we're able to go 6 times 1/3 u cubed from 0 to 1. And we're able to just plug in 1 and get 6/3, which is 2. So I think in the end here we have a value of 2 overall. Here, I'll check my notes and make sure that I didn't lead you astray. I think that's good. Real quick, go into GeoGebra, hoping that this works first time. GeoGebra, you're killing me. Wait, if I just go M, never had to do this just to get the thing to load. Okay. Basically, what's going on here is we've got this vector field in the background. We're traversing our curve in a clockwise fashion. And yeah, along the way, each one of these values is given to us by a dot product between these two vectors. So you can see as the dot product, I don't know, let's scoot back here. The dot product here is 0. So red means 0. When we get out to like these blue values, it means that these are the dot products getting big. And then that we down and go approach 0 again as we get to the end. But yeah, it's the dot product between the force field and the displacement vector that's giving us our work each time, the work that's being done by the force field. Super cool. Okay, that's that one. And the last one, finale. Yeah, it's 12:20, and I haven't even started uploading this to YouTube yet, so we're gonna be a little bit late. Okay, for this last one, to save time and to realize that, yeah, I don't know. I'm not gonna. Let's just take a look at what I did before. Oh, the scroll wheel. There we go. Oh, my Lanta. Okay, example 5. Yeah, if we've got this vector field and it's simulating some kind of fluid flow, yeah, we're given a potential function, x, y, z, and we are determining the fluid's flow along this curve. So we're taking the dot product between force field vectors and displacement vector. In this case, we've already got R of t parameterized. And so if we're going from 0, 0, 0 to 1, 1, 1, That means we're going from t equals 0 to t equals 1. There is our force field vector, because we're just plugging in all of these into this gradient function. So we get a bunch of t things. Here is r prime of t. Multiply those, dot product those two vectors together to get these. We get 6t to the 5th, and integrating, we get 1. So, woo, in the end, the sum of the fluid's flow along that curve is 1 with whatever units we're using. We're mathematicians. We don't care. No, you guys you'll care. Anyways, yeah, that was 2 sections in one go, 15.1 and 15.2. Yeah, I'm still tossing around the idea, but I think I might try to give you extra credit for doing the activity that I have set up for these. It might also involve watching a video on section 15.3 on the fundamental theorem of line integrals. Yeah, I don't know. Maybe yeah. I don't know. I think that this stuff is really cool. It's actually really applicable when you're working with vectors, which I'm sure you guys will be. So that was vector fields and line integrals. Line integrals are so cool. All right. We'll see you on Tuesday, and we'll do review and a test then. This stuff will not be on that test. All right, thanks. See ya.